There's a vector space V, not necessarily a column vector, and then we fix a basis B. If V is a column vector space, Rn, B can be E1, E2, E3, but doesn't have to be. You can choose different bases just like we did it here. V1, V2 is a different basis. V1 is 1, 1, V2 is 2, negative 1. And then a matrix associated with that looks different, right? But if it's not column vector space, to bring out a matrix, you definitely need this basis, right? With that basis, and this is a basis, and endomorphism V is, you know what the endomorphism V is, right? It's a collection of all linear map from V to V itself. But each of the endomorphism, I pick it here, endomorphism from V to V, then there's this basis, right? Then you can look at the coordinates, not abstract vectors, coordinates. So here, each of the vectors written as AV1 all the way up to ANVN, and where that one is going under this map ST, then that's totally different coefficients, right? So what happens is that this A1 A through AN is multiplied by some matrix M. Although this is not a column vector matrix, will get you this V1 to Vn. So here's a B1 through Bn. Does this description make sense? This entire thing is not a column vectors, but if you just look at the coefficients, what happened to coefficient is really what is happening to the column vectors. So I've collected this coefficient, and what is the matrix that takes this coefficient to the target coefficient that is rises from potentially abstract vector space? That's the matrix, right? So do you see that each of the map, there's a matrix, right? Each of the linear map, there's a matrix in there. So what is that? Is that matrix n by n, whatever the field that you're looking at. Is that okay? All right. So is there any problem with this? I described it as a phi. Remember phi? Phi was L of VW. Then it was a matrix of n to w and things like that. Well, it was actually L of Rn, Rm. It's more specific. Any linear map from Rn to Rm is described as a matrix. Now, even if it is abstract vector space, you can still describe it as a matrix, right? And this is, and phi is, what kind of linear map is it? This is a vector space, right? And this is a vector space. Do you remember the dimension of this vector space? N squared, thank you. That was the dimension of this vector space. And therefore, this is the dimension of the vector space. If phi is what kind of linear map? Invertible. Isomorphism, right? It's an isomorphism. Difficult world, it's just vector space of linear maps, right? But if it is injective, and if it is a surjective, and if it's linear, and the way that it behaves is exactly the way this guy behaves. Here, phi is an isomorphism. Yeah, phi is an isomorphism. Therefore, dimension of that and dimension of this one is equal to that. All right, still I'm using this. Choose a basis and what is happening to the coordinate map. I brought this up not only because that's what we just did. It's a summary of what we just did, right? You choose a map, and there is actually a matrix associated to that. Number 3 is an example of, of this thing. Make sense? All right. Then the reason I brought this up is that the way this behaves as a linear map is kind of the same because of this isomorphism. And you accept that if I have matrix M and matrix N, then as a vector space, we have A times M and B times N if this is coming from matrix world. Right? Scalar multiple and addition. Isn't that the vector space calculation? Right? But we can also multiply this M times N. Isn't that right? What is the meaning of a multiplication? Why did people even think about multiplying two matrices? And you practice how to multiply it. Matrix multiplication here, what is the multiplication changed what word in this world? C word, right? M is coming from some sort of linear map. N is coming from some sort of linear map, right? M times N is another matrix, M prime. Then what do you do with S and T to get this M prime correspondence map? C word, composition, right? All right, so if you believe what is happening in here as a map and as a linear map, if it's the same thing, you will believe that, okay, this multiplication is really lifted up here. The composition must be treated as a multiplication. Okay? So although the correct word to describe here, if I have two maps, S and T in endomorphism, correct word to describe the ST is S composed with the T, right? But this really means that S composed with the T. This is the correct notation, but they abuse now just ST, right? Because it works just like these two matrices multiplied to each other. All right? You don't multiply two vectors in a vector space, right? But now we're doing that. That lifts the structure from vector space to something else. That is called ring in abstract algebra. But it is more than a ring. We also multiply some coefficient to that one, right? Ring is just a multiplying object, but an additional structure of a scalar multiplication, that is called algebra. Algebra is a set with a vector space structure, and you can multiply those vectors, and you have a way to understand that, and then scalar multiply there. That is algebra. So this is called matrix algebra. We thought that matrix algebra is an action, is an abstract word. Now, when I say matrix algebra, is a set, right? The met itself is now called vector space, and now it's called matrix algebra. Now you do the same thing. This was the vector space of endomorphism, right? Now we can multiply these two abstract vectors like that and get another endomorphism. Therefore, this is called endomorphism algebra. In vector space, you don't multiply the vectors, but now you can do it because it has a richer structure. All right? Now they introduce here, if I have m times m, nobody raised any question. I know what it means, mm, m squared, right? But here we do the same thing. It's a mirror image in this abstract world. If I have t, then tt is a t composed with a t is a t squared, right? That's a new notation I'm introducing here. When you look at t squared, this is not like a polynomial t squared, but it's a t composed with a t. What is it? Through this basis, we have a matrix, an m times m matrix, that you can kind of visualize what is happening in t here, t squared. All right? Now you think about all sorts of things. M third plus m plus identity matrix. No problem. Nobody has any difficulty with thinking about this one, right? Matrix multiplied to itself 3 times, plus the matrix itself, and plus the identity matrix. And you do have a same notion, such as you compose with a 3 times and add it to itself and plus 1. Do you know where this one sits inside? This is sitting inside endomorphism ring, right? Over V. If I choose a T, you can do this thing now. Compose it as many as you want. Still, it's an endomorphism on V. All right? This is not a vector. This is not the vector. The element is not a vector inside V, right? This is the linear map itself. All right. That's the section. Polynomial applied to operator, whatever the section in that chapter in there. Okay. So I want you to be freely think about, right? Not necessarily going through matrix world. If I just choose any linear map And you can do this type of thing. It looks just like a polynomial, right? Yeah. So it actually has a polynomial structure. And you know what it means is to multiply 3t cubed plus 3t and plus I, like that. Right? Make sense? Yeah. So next thing I'm going to do is something that you've seen for a long time, but it is an amazing thing. If you think about how they do this in a differential equation, think about this is a differential operator on the space of functions, right? So this is a differential operator. You can go do something like this, t squared minus t plus 2i. You see what that map is? T, do it 2 times, right? And minus t and plus 2i. But whenever you see these things, something triggers you that what to do about this map. If it is a polynomial, what would you do? You're going to factor, right? But I'm not just going to factor. I'm going to justify this thing correctly. Because it's not the same old polynomial. To factor this one, you actually have to, knowing that t minus 2 is a factor, right? So you actually have to pull out, and we're going to do t squared minus. One way to justify what we're doing in our mind is actually true. If it's negative 2i, what would you do? That's going to be, wait, did I do this correctly? Negative 2, the negative 2 is correct, t minus 2, to pull out negative 2. What should be this one? Oh, positive 2, and plus ti. 2i, is that right? I did something wrong. This is really, it doesn't factor. It should be negative, that's why it's wrong. It should be negative I. Sorry about this. Nothing wrong, right? Is that okay? The negative t is negative 2t plus t because it's a vector space. Endomorphism, before we do the algebra, is a vector space, right? Correct? So negative 2t plus t is negative t. Now, this, I hope you see this. This one is actually like this, and I'm going to do it like this, plus t minus 2i. You can factor out t like that, and you have to make sense out of it. Is this t squared minus 2t is really same as t minus 2 first, and composed with the t. That's how you justify it, right? But 2 sounds weird, right? 2 is not an endomorphism. If you factor out t, what should be the good operator that should remain in there? Identity operator, right? Invisible identity is there in that invisible one. So nothing happened to that part, but something happened to you have to justify it, not because you can just do it like this polynomial. You have to justify these two maps are the same. Or how do you justify that? Just to do that. Here, this is a composition. You apply some vector v, and you calculate it, and you apply some vector v here, and calculate it, and show these two things end up exactly the same result, right? Then you know these two operators are really the same. Because what these are is the compositions. So let's do this one. What is this? This t of tv minus 2v. Does that is from the definition. We have to apply v to the inside function first, and then outside function. That's the composition. So I applied inside function first, right? Then I'll apply the second function is a t squared v. Is that right? 2 times t, and this one is at 2 factor out because it's linear property. 2 is a scalar. It's t of v. But if you apply v squared here, of course that goes in there and like that. So these are the same. That's how you justify the thing that you wanted to do is actually true as a map. That actually is the same thing. Now, if you could factor out common thing to the left or right in the correct order, you can do that here too. That you can factor out t minus 2, right? You can't factor out to the front. In general, no. You have to keep the order. ST and TS, that's a different. right? This is not a commutative ring. Therefore, when you factor out, you have to factor out in the correct order. So t is staying there. You factor that out. What's left here after you factor out the whole thing is identity there, right? And you have to factor out t minus 2i in there. Right? So this operation can be factored t minus 2i first and then t plus I later. Then you can show that these two things directly, not going through factorization, directly, these two things result in the same. You apply v there. By definition of this composition, you can show these two things are the same. So it's a deductive method of doing that. But if you have to show this map is equal to that map, all you have to do is apply v and expand as much as you can and show these two results are the same. Then you show these two things are the same. So if this is a linear operator, differentiate it 2 times, differentiate it 1 time, and do not differentiation. So this is like y double prime minus y prime minus 2 times y, right? And this factors like this. Amazing. So what kind of functions, after you differentiate it, becomes 2 times itself? What is the solution of this differential equation? This is e to the 2x, right? This is simple. You do that even in Calc 1. And this one is coming from t to the negative x. And that's why that characteristic polynomial of differential equation works in that way, because of this factorization is available with a constant coefficient of a linear. When this is a non-constant, then factorization is still there. It's a lot uglier, right? So here, the book, if you read the book, you really have to carefully read the book. You try to avoid this matrix algebra and try to stay in this world. In this world. Whole book is exposited in this way so that you get used to this endomorphism algebra. But whenever you're entering the new concept and something harder, then it's easier to kind of translate it into matrix algebra and see what is happening there and get a better idea and kind of translate it, everything in terms of this endomorphism algebra. So I'm going to do myself in here, try to everything in terms of this endomorphism algebra like this. But it's what's really happening in here. But what I want you to not do this one is that whatever he's doing with that in terms of algebra, I don't care. I can do this matrix algebra. So I'm not going to listen to this side of the exposition. I'm just going to stick with matrix algebra, matrix algebra, matrix algebra. Well, then it's just matrix algebra. You have to get used to a little bit of abstract idea like this, so that when we talk about infinite dimensional vector space, then there's no matrix algebra. You have to rely on this type of language, which is Hilbert space. Hilbert space is a language for quantum mechanics and modern physics, right? That is infinite dimensional vector space, and they have to rely on this type of endomorphism algebra. So it's hard to read because it's abstract, but it's something that you have to get used to in this level. All right. So